Hello, and today at Uncle Data we have Robert Hodges, who's a CEO at Altinity, and Altinity is a company who's focusing on ClickHouse, and ClickHouse is an OLAP database. And what's the difference between OLAP and OLTP, and what are these acronyms I'm talking? We're gonna dive in a bit later. So, Robert, I guess. You're not how to say in Europe. I'm not sure how many people know you, and for my listeners, I noticed that you gave a keynote at OSA conference this year. So can you share a bit more about your background and experience and how you ended up in data area in general?
Sure. Well, first of all, Thomas, thank you so much for having me on your podcast. Yeah, it was kind of an interesting journey. I think most of what I've done in computing has been just a matter of being at the right place at the right time. I started programming over 50 years ago. I was a kid in school, and we had a computer, and you could use it to program BASIC. So that was the first language I learned, and just because it was there. And in the same way, when I was actually became a professional programmer starting in 1980, about 2 years in, the place where I was working introduced a database called M204, which was a very popular database at the time, used largely by the United States government. And I had no idea what it was, but I was sort of fascinated by the fact that you could stick data into it, you could get data out, and then if you looked a little bit about how it worked, it had this very complex structure that allowed it to retrieve data quickly. It was using inverted indexes, and I the more I looked into this, the more fascinated I became, and I decided I wanted to work on databases, and I've sort of been doing it ever since. That was over 40 years ago, and I'm still doing it today.
Oh, that's interesting. Basic, actually, the fun fact also that when I was starting at school, and my father is like a programmer as well, and he is like, okay, so now you're gonna learn basic with the loops, So went over that. It was like interesting experience, like with trying to print out. You enter a number n, like as a kid, right, and then it prints you a tree of stars, like
Mm-hmm.
increasing in number whatnot. So that's nice experience. I
Yeah,
see actually that uh, a lot of my first things kind of matches yours, right? Because like we
yeah,
talked before the briefing, before the recording, that you worked at Sybase, and that was actually the first database I was
right.
checking into as well. So interesting.
Yeah, yeah. Now, when you were programming BASIC, though, I suspect it was a little bit different because you were
Of
on a
course.
like a PC, and you probably didn't have to type line numbers beside
Yes,
the.
I had. I
Oh, you
had.
did? Oh, okay,
Yeah.
wonderful. Okay, that's okay. Yeah, because my first basic programming was on actually a teletype, and connected to a time sharing service of a 300 baud modem. It was really, really primitive, but it was fat. But it was, for a kid, it was just like this machine you could play around with, and you could do anything. So it
Yeah.
was really fun.
Yeah, if you miss a line, you want to insert it so you don't have to put an order. Instead of, 10, 20, 30, you do 12,
15.
13,
Yes,
15. Yeah,
exactly. Exactly. Yeah.
nice. So, like, as I saw, you went over, like, you mentioned yourself, you were looking at databases, right, from different angles and perspectives. And you settled at ClickHouse, right?
Right.
Any particular reasons why, or like some specifics you liked?
Well, yeah, again, ClickHouse was a bit of a matter of chance. I've worked with a lot of different databases, about 20 of them, and some I worked for years, like MySQL and Sybase. Others, like DB2, I worked for 2 days, and it was enough to realize I hated them. And so with ClickHouse, what happened was I have a good friend who's the CTO of Altinity. He and I met about 20 years ago, and in a company that didn't go anywhere. So we went our separate ways, but we stayed in touch and stayed friends. And a few years ago, after I was running a startup that we sold to VMware, and so I was working at VMware, and Alexander Zaitsev, our CTO, he called me up and said, "Robert, I know you like databases. I have one that I really think you should look at." And I said, "Well, okay, I'm busy now. I can't really do it," and because I was, working at VMware and wasn't ready to leave. But when I finally looked at it, sure enough, it was a really, really great piece of technology. So what impressed me was that it was very much like MySQL in the sense that it was open source, could run anywhere, and spoke SQL and was very versatile. But it was an analytic database, so it could deal with billions of rows almost effortlessly. So it's a columnar store, which is very efficient for reading data, very high levels of compression, very high levels of parallelization. And what was the clincher for me was it's also relatively simple to start it up and use it. It's just a single process, like MySQL, and as a result, it looked like a database would work really well in clouds. And I was at VMware at the time, actually in a division that was helping VMware users build private clouds. So this looked like something that would fit right in, and we could run in VMware clouds. That's where I got the idea of using it. So long story short, I left VMware. The company that Alexander was running for needed somebody to run it, so I took the job, and we've been working together on ClickHouse ever since.
Nice. So it seems like you mentioned before, it's a bit of a matter of luck and knowing people, right? When all things interconnect, one step after another, and you're here, right?
Right. And I think curiosity, and because obviously the things you encounter a lot of things, and not all of them are interesting, but this one really was. And I think the other thing that I really like about ClickHouse is I'm personally very interested in distributed systems, sort of the notion of a bunch of services that are connected over a network and work together to get work done. ClickHouse is a distributed system, and it actually uses distributed algorithms in many cases to get work done. So it's personally very satisfying to work with, because I just like that kind of problem, and some of the solutions in ClickHouse are very elegant.
No, that makes sense. I'm thinking, right? So we mentioned, OLAP. You mentioned, like the columnar store, right?
Yes.
Can you share from your experience, and you mentioned, and analyzing billions of rows, running it effortlessly. From your perspective, like short intro for people who don't know or listening to this podcast, what's the difference between actually the OLAP system and OLTP?
Yeah, great question. Well, first of all, if you just back it up, there's something that I call the fundamental theorem of data, which is that the location of data is everything. This is the thing that determines what is fast, what is not fast, what can you do efficiently, and what's not efficient. So, in a nutshell, OLTP databases that stands for online transaction processing, and the data is arranged in such a way that you can change individual records very, very quickly. And the way to do that is to store them in rows. And so you think about a table, think about that table perhaps contains sessions for people on a website. So if you want to they do something that changes their session, for example, add something in a basket, you want to get into that session, change it really quickly. Moreover, you don't want to lose the data or have sort of have other kinds of accidents that might cause you to lose track of that user. So row-oriented databases, and these are databases like MySQL, like Postgres, like older databases like Oracle as well, have this format that allows them to very quickly make these transactions where they add things to the database, add sessions to the database, change them, take them away. So and they can do this. Sometimes you can have hundreds of thousands of connected users who are doing this simultaneously. OLAP databases, by contrast, are designed to read data. OLAP stands for online analytical processing. And the idea is you may have enormous pools of data, so tables that might be trillions of rows long, far too large to fit on a single machine. And the idea is that you're going to come in and you're going to be asking questions about the data, and those questions are difficult to predict in advance. So the OLAP database example I gave, online sessions, the OLTP example I gave is online sessions. In OLAP, you might be actually tracing the history of those sessions and everything that happened to them. Like where did that session start? When did it start? Did they buy something? So the online analytical databases almost universally use a columnar format. So instead of storing all the rows in a single place, they store the columns in a single place, like arrays. And this means that you can, when you do queries, you only need to read the data that you refer to. So if you have 100 rows or 100 columns in the tables, you refer to 3, you only touch those 3. So you can scan the data very quickly. It also allows it to compress very well, which means that you scan less of it. And finally, when you use this arrangement of data, it lends itself to parallelization so that you can apply enormous resources to it. The result is that you can often get answers back from to complex queries in a fraction of a second because of the arrangement of the data and your ability to apply compute to it to get an answer quickly. So these two databases tend to have, they're sort of really, in summary, the online transaction processing tends to be row-oriented. It's designed to do a lot of little transactions very quickly, very safely, not lose data. The online analytic processing is the flip side, designed to read data, answer questions that cannot be predicted in advance, where you have to scan large amounts of data quickly.
Yeah, so I guess the good analogy is like the CSV file for row-oriented files, right? Because you have to go row by row and
Yes.
search, where actually what to change and where. So you read the row on the key, and you go column by column where to update.
Right.
I guess the downside of columnar databases are actually the updates, right? Because you have to do a quite heavier action to figure out everything and then update it.
Yeah, and in fact, every single person that starts with OLTP databases and comes to an OLAP database that's arranged in columns, probably the first thing they'll do is they'll start to enter the data a row at a time, because in MySQL or Postgres, this is really fast. Well, and then, the database is slow as molasses. Why is that? Well, if you have 100 columns in your table in ClickHouse, you're going to actually have to write 200 files to create a single row. That's just really, really slow. And so you learn pretty quickly that, okay, we need to add rows, maybe 1 million at a time, and then it's more efficient. So there's the big differences, and it takes a little bit of getting used to.
Yeah, that's true. Another, I think, difference is that, at least to my experience, not all OLAP databases has indexes in general, and all OLTP has, right? That's, I guess, one also, and the index types, I guess, also is different. As far as I know, in the usual like OLTP systems, it's a B tree, if I'm not mistaken.
That's
the usual
very
approach
common,
on the indexes.
sort of B tree or B plus tree. Yeah, right. So you're, and it has something. Some of it has to do with the evolution, but very, very typically, there's two reasons that the OLTP databases have B tree indexes. One is that they use them to find the individual rows. So B tree is designed to allow you to read the minimum number of blocks from storage before you actually arrive at the row. And this dates back decades to a time when storage was both slow and expensive. So that the OLTP databases are optimized to do this efficiently. The other thing that you do with indexes in OLTP databases is they're actually used to enforce referential integrity. So, for example, when you have a unique key on a primary key, which is by definition in traditional databases a unique value, the index can only have one entry at the end, and it enforces uniqueness. So that's how the OLTP database can detect that you're trying to put two rows in this under the same value. So OLAP databases don't use indexes in this way because the idea is to scan data very quickly. And first off, in many cases, you don't need an index at all because you're scanning only a fraction of the data since you're only looking at columns. If they are compressed, it might be a fraction of a fraction. So compression levels in some cases can be 99% or more. Moreover, as I've mentioned elsewhere, you can parallelize that. So when you ask a question or look for values in a column, you can just do a brute force scan and look at every single value in the column very quickly. You don't need an index. So that's already one major difference. The second thing is when you do need indexes, we have a couple different varieties. We have what's called a sparse index. Confusingly, it's also called a primary key index in ClickHouse, but it's used to locate values within the table. It's typically very simple. But unlike the B tree, which has an entry for every row in the end, ClickHouse primary key indexes on average have an entry for every 8,000 rows. And the reason that this index we call this a sparse index. The reason it works like that is to keep it small so that it will fit in memory when you have a trillion rows in the table. So we have that kind of index, which means we can quickly locate the block that may contain a particular row. We're still going to have to scan, on average about 8,000 values to find what we're looking for. But that's like a second way of locating things. And then the final thing is we have what are called skip indexes. So when you're doing scans, the idea is to knock out in advance rows, places to look at so that you don't read as much data. And so skip indexes might say, hey, within this part of the table, tables are divided up into parts. You're only going to see integer values between 25 and 50. So if the value you're looking for is outside, you don't even need to open up that part. It's simply not going to contain it. So these are different examples of the indexing. And again, everything that we're doing in the indexes is designed to make these scans more efficient so that we don't have to open up and read blocks unnecessarily.
Yeah, makes sense. I guess it's very similar to how like Parquet file reading is done, right? Because you have the metadata
Correct.
part,
Yep.
and you can read, what to skip, what not. So partition pruning and these kind of things. That's an analogy. Okay.
In fact, the underlying structure of ClickHouse tables is very similar to Parquet, and as it turns out, ClickHouse is very quick at reading Parquet. So ClickHouse can read external Parquet files, and the model is very well suited for ClickHouse processing.
Yeah, if it's architecturally similar, then it's very easy to adjust, I guess, to do the same. Since you mentioned, the traveling part of like data locality, right? And we're talking about, external tables and these things. So also I checked that ClickHouse is actually storing, even if it's distributed, it stores some information on disk on the specific machine. Am I right on this? How does the data storage work there?
Yeah, actually, could you repeat that question? I think I missed a
word. How does the storage under the hood works in ClickHouse? Does it store on the machine disks?
Yeah, actually, it works in a couple different ways. So when ClickHouse was originally designed, it used what was called a shared nothing model, which meant that a ClickHouse cluster, even a cluster of say one server, but arrange up to hundreds, consists of servers with their own separate storage, and with those servers connected over a network. So when you run a query, you would dispatch the query. You would arrive at one server, and you would issue your select, through the connection, ClickHouse would break that up into subselects, which it would send out to all the other nodes in the system. This is called federated query, and each of those nodes, when they get their piece of the query, they'll run it, perform their computations, for example, averages, histograms, whatever you're looking for, and then they would stream their partial results back to the initiator node, which would do the final, merge the data, sort it, hand it back to the user. So, in this particular case, the tables are stored just as files on disk, and or SSD, as the case may be, and in a structure that was actually quite easy to understand. If you had a database, that was going to be a directory on disk. If you had a table within that database, that was going to be another directory, and then you'd have parts, which are chunks of data in the table. So you could just go in and you could look at it, and it was very straightforward to understand. Now that architecture is versatile and very effective up to a point, but what happens is, as data sets become very large, and particularly you don't look at them very often, it's also very useful to be able to store them in object storage. So this is storage that is visible, accessed across a network, is visible to all the nodes, and allows you to do two things. One is it allows you to store data very cheaply, because you just put a single copy of the file in object storage. It can be shared by all the nodes. The other thing is it enables is what's called separation of compute and storage, which means that you have the data in one place, and then you can scale the nodes up and down to according to how much compute you need at any given time. There's actually kind of a middle ground on this, which we use very heavily, and that's to use the original model where each database has its own storage, but to put that storage on something like Amazon Elastic Block Store, which means that it's across a network, and as a result, you can dial up or dial down the VM size that you're using to process that data. So that also gives you separation of storage and compute. So there's really three models of how ClickHouse can handle storage, and they're all used. They're all appropriate for different for particular use cases.
That's nice. I didn't know about that, because it's like you have the all flexibility, right? You don't have to push all the data to the nodes, so you don't have to worry about the disks being filled and whatnot. You can split things there, what's needed, what's shared, put on the EBS, and scale up machines if needed, or add more information to the EBS. So it's
EBS has been a real game changer. I think EBS and block storage, I think this is just particularly in cloud systems. And EBS is amazingly capable. It used to be slow, unreliable, not anymore. It's in effect, it's actually as fast as SSD in many cases. Which people think, hey, SSD, that's the cat's meow. You always want to have your data there. Well, the answer is not quite, because EBS is also extensible. So the cloud block storage, you have a terabyte of data. You decide that you need more. You can just extend the file system, and this can be done in if you do it properly, it could be done without having to restart the VM and while other processing is going
on. Nice. Yeah, because I was thinking, if you have a predetermined size of your cluster, right, and you see that you need more data, right, so either you append a new node, right, to your cluster, where it can be, then all of the data will be split or reshuffled, so it will be balanced across the nodes, or you could add a bit more disk size to each of the machine and then extend it, but it has limits because it's virtual machines, right?
Yeah, and the most common way that data grows in ClickHouse data warehouses is people need more. They need more storage. So, and what's interesting is we have users that grow from, they might start out small, maybe a terabyte to begin with. Before long, if their business are growing, they may find they have 10 or 20 or even 30 terabytes of storage attached to each node through EBS, and this can just be smoothly by extending the volume sizes, you can just grow with the needs of the data set.
Nice. I guess, like offloading to some external places also helps with, like you
Yes.
mentioned, the data
Yeah.
hoarders.
Yeah. So actually, what ClickHouse also does is what's called tiered storage, where you can actually keep a fraction of the data on very fast storage, say SSD. You can put it onto slower storage, like sort of cheap versions of EBS, which can be extended, and then from there you can even put it into object storage. So that's called tiered storage and is quite commonly used.
Nice. That sounds really like a neat feature, for the people who are like wants
Yeah.
that flexibility and not tying them
Yep.
up
Yep.
for this.
It is very ClickHouse is very. That's another thing that's a strength of ClickHouse. It's very flexible.
Yeah. So I'm thinking, you mentioned, like data inserting, right? Is if you insert row by row, right? It's
Hmm.
heavy and it takes time, right? It's not that efficient. So let's talk about that part and like all of the the management. Like we need real time now, right? So
Hmm.
how does ClickHouse deal with that? Because as you mentioned, right, it has to write 200 columns, it has to write to
Right.
200 files, right? How
Right.
does that being handled?
Well, the first thing is you have to help ClickHouse a little bit. So don't write a single row at a time. Write millions. And this is actually not that hard to do because the types of applications that ClickHouse works on are things like security, event, and incident management, where you have for example, a multi-tenant system that's reading data from a large number of data sources and inserting the events that it sees, often at the rate of millions or tens of millions per second. So you have very large volumes of data arriving, and you insert them in blocks of, say, like a million rows or more at a single time. So when you do that, ClickHouse can actually write to storage in parallel and very quickly. So these blocks are loaded into memory. They're constructed, sorted, and then they shoot out to storage. So that's the first part, is to write large blocks and let ClickHouse add many rows at once. In this case, having a large number of files is less important. ClickHouse also has variants on its storage, which don't require it to store like necessarily 200 files, but maybe just a few in a format that looks more like Parquet. The place where it gets complicated is updating. So, and ClickHouse is, like many OLTP database, or excuse me, OLAP databases, has made some design choices that are really optimized for data that's not changed very much. And if you think about it, this makes sense because, again, in a security management system, you're monitoring events, which are just records of things that happen, like weblogs, for example, that happened out in the real world. And once you load them, these things don't change very much. What really happens is that they are loaded into the database. They sit there in their original form until they time out. So you might keep them for, say, 7 days, at which point you want to delete them automatically. So ClickHouse, for that particular case, that's an example of time series data with a retention period. ClickHouse has very efficient mechanisms for keeping them for X number of days or weeks or months, and then dropping them automatically. Where it gets complicated is if you have, say, a trillion rows of data, and you decide, hey, one of these values is not formatted correctly, or I want to make a change, like the organization that this data belongs to has changed, and I need to go to every single row and update it. That's a more complicated problem, and ClickHouse is less efficient on those types of changes than it is on inserting and just deleting when things time out.
Ah, okay. So my question kind of looks like that. Like for me, it looks like that ClickHouse very prefers to work with. Before I ask and formulate my questions, what about the joins? Because the joins on all OLAP systems is also quite a painful part, right? Because it
Yes.
utilizes a lot of CPU
Yes.
and it has to do things in memory. So is that handled in ClickHouse?
Yes, ClickHouse can do joins. That said, it's when you build these types of systems, you tend to try and do as much processing as possible in a single table. And the reason for that is that if you do arbitrary joins, particularly between large tables, a couple of things happen. One is the queries are more complex and they may have to scan the data multiple times. So there's there's a lot of questions that you may ask that even on data that's in a single table, you may have to scan the table multiple times and join the results from those queries. Those are called self joins. So ClickHouse tries to avoid those, and actually, or allows you to avoid those. They have some really neat features that allow you to avoid these self joins and just get all the data in a single scan. Why is that important? Speed. So if you can get the data, in the applications that we're helping people to build, you typically want to have very consistent response time. Like somebody's looking at a dashboard that shows, again using the security model that shows the state of information being scanned. You'd like that dashboard to always come back in less than a second. So scanning, just doing a single pass through the data or some fraction of it, is the way you get that fixed latency. So that's the first reason why this format is preferable. The second thing is if you have joins between very large tables, those tables can't fit on a single machine. And as you begin to join, you often have to do what's called shuffling, where you'll scan the data and then you may actually even have to move it between different machines so that the parts of the table that are joined are present on the same machine and those rows could be matched up. This is complicated to do. It's also slow, and worse than that, it's unpredictably slow, because depending on how much data you have to move, where you have to move it, the queries can be take greater or lesser time. There are other databases that do this very well. BigQuery from Google is a really good example. It handles that problem very well. Snowflake does it well, but it requires a very sophisticated query analyzer and the ability to move data efficiently between machines to get this to satisfy these to get things to join up properly.
Yeah, and that's what I was leading, right? So it looks to me like that most of the OLAP databases in general, they kind of tend to prefer to work with a single table or to minimize joins, just to minimize the joins and shuffling of the data underneath.
That's correct, and it really depends on what you're trying to accomplish. So in ClickHouse, there are many use cases that ClickHouse handles very well, but it's particularly salient in what we call real-time analytics, where you want to get an answer back very quickly. Think about something like Google Analytics, which is used to analyze web traffic. You come in and you're just asking a bunch of, you come in and you maybe get the list of your web pages, and you want to see, okay, what was the time on page for, ordered by web page. Okay, now that I have that, let me go ahead and further subdivide that by region or by browser type or other types of characteristics of the web page. These are called slicing and dicing queries, and you can think of them as taking different slices of rows in this very large table. So that particular table organization is well suited to things like weblogs, which is where this information is coming from. So or where these query results are coming from. So it actually works. When you're in BigQuery or Snowflake, what you're sometimes doing is doing asking questions that are less predictable and require you to bring together many different data sources. That's a really different problem from just populating a dashboard. You're asking sort of a very open-ended question that might scan, very disparate data sources, like information about support, information about sales, sentiment data from, coming from Facebook. That's a much more amorphous type of question, and really requires a database that's optimized for a different type of query to answer effectively.
Oh, okay. Since we're talking now about the different types of databases, right? So I guess from what you mentioned, right, usually you can have then couple types of OLAP databases or OLTP, depending on the problem you're actually trying to solve, right?
Right.
So
That's yeah.
yeah, did you start?
Yeah, that's absolutely correct, and I think that's definitely a change that's happened in the in the last 20 years or so.
Yeah, people not trying to to smash everything with a hammer, and everything is not looking as a nail, right? Sometimes you have a screw, let's say, right?
Right.
So that makes sense. So we talked about I scratched this topic, and let's talk about a modern data stack, right? Where people think that actually they have to use one specific type of product, right? And there are new coming in. I think it's Apache Doris, which is also trying to break everything. Oh, we're doing everything better than, like, let's say, 3 different tools and whatnot. So what do you see as or where should people focus when choosing their modern data stack? What are in your eyes the most
Yeah,
important criteria?
I think that that's a great question. And generally speaking, particularly open source databases, they tend to focus on one particular problem as opposed to being really general purpose. Snowflake is a good example of a proprietary data warehouse that does try to be actually a bit like Oracle, not surprisingly, because the folks that wrote it originally came from Oracle, but it tries to be a database that can handle a wide variety of applications, not necessarily well, not necessarily cheaply, but if you're going to pick one database and just have it work for all the OLAP applications in your company, Snowflake is probably a pretty good pick. And that's one reason why it's very popular and why people tend to choose it. Open source databases tend to be more fit to purpose. So, for example, there are if I'm building an application building a modern data stack, I might have 3 choices of database, and depending on my what I'm doing, I'll pick one of them. So, for example, if I'm doing processing documents, uh, and where I want to load them in and then be able to general search on the document text, I might use OpenSearch, which is the fully open source fork of Elasticsearch. If I'm searching for data that's stored in data lakes or across a wide range of data sources, I might use Presto because it does federated query very effectively. If I'm doing real-time data, for example, valuing securities in markets or log management or observability, sort of rapid query on observability data, I might pick a database like ClickHouse, a real-time analytics store. So you tend to pick something appropriate, and then that's sort of more focused on the niche you're attacking. Pick that database and use that one and use that as a foundation for your stack.
That's true. So focus on the problem instead of finding a unique or single source solution. I'm
Right.
thinking of
Right.
thinking about the why people tend to choose a single solution is that they try to maybe minimize the administrative work, right, or support work.
Yeah.
How big of a effort is on ClickHouse to actually maintain?
I think actually, just looking at going back to Snowflake again,
Mm-hmm.
one of the reasons that people choose that single database is it means there's one thing to learn. So, for example, a company might pick Snowflake, and that way all their developers learn that one database, and then they can all work on applications. They can sort of move between applications. They can do new things. With ClickHouse, its behavior is radically different from OpenSearch, for example, or from Presto. Moreover, in all of these in open source databases, it's quite common that you have to have some real insight into what is going on under the covers to use it effectively. So ClickHouse, again, to use a specific example, does not have a cost-based query optimizer. It will not automatically, figure out what's the most efficient query based on the distribution of your data. Another example, ClickHouse will not automatically ClickHouse has brilliant compression, but you actually need to make some choices to use it effectively. So that means you need to know how ClickHouse works inside. And if you have that knowledge, when you now come to a case where you're reading off data lakes that's more suitable for Presto, your ClickHouse knowledge doesn't transfer very well. So people, that's a consideration. When you're picking the databases, how much do you have to know? How much do you have to know about the insides? Open source products, as I say, tend to require more internal knowledge than some of the proprietary solutions.
No, that's true. You have to go into the code if something is not working, as you expect, and maybe want to contribute as well. So that's a different thing.
Right. But if you're building, we have customers that run ClickHouse servers with hundreds of nodes, and in that particular case, it's brilliant. You're building a very large cluster that suits a single purpose. You don't need to solve a bunch of different problems. You just need to solve one, and you need to solve it super well. ClickHouse does that far better than Snowflake does.
I'm thinking then, like if you learn things under the hood, right, for specifically ClickHouse, right, or in general for any of the open source tool, I guess that makes you a very niche type of specialist, right, where you specialize, because a lot of people tend to be generalists, and if you go deep on that niche, right,
I think what I would say is it forces you to know more about database internals. In the end, there's only a certain number of things you can do to arrange, a certain number of ways you can arrange data. There's only a certain number of ways you can access it. So if you have that knowledge, that database internals knowledge, you can actually move from one database to another fairly quickly. So I often do talks where, in fact, I've done this many times over the years. I'll do talks where, the topic will be sort of like, hey, use your MySQL knowledge to turn into a guru on Cassandra. So Cassandra is very different from MySQL, but if you look under the cover, you can actually associate concepts in Cassandra with things you already understand from MySQL. So the knowledge is transferable. It's just not the same. You just have to. They're different products, right? And you have to learn the specifics of each one.
Oh, and that also fits nicely with like the, let's say, older approaches where you had like only relational databases, right? The physical DBA and logical one, right? Where you define a model and then you define it as a table, as a DDL, and then figure it out, the indexes and whatnot. So it is actually the same, right? You have to know how to arrange your data before you actually put it in, so your ClickHouse would run efficiently.
Yes,
that's
exactly.
A neat thing.
Yeah. You have to know how it's stored, and and that's So ClickHouse is more because of the types of applications you're writing, is very sensitive to the location of data, and you have to make good choices. That's otherwise you may regret it.
Yeah, you might make some costly or like long running mistakes, right?
Yeah, and this is actually not uncommon in particularly in these large data warehouses. Once you've arranged the data, for example, really simple thing, once you've chosen a sort order on the table, that's a very basic choice. Once you've done that, you're sort of stuck. The primary sort order of the table, that's going to stick with you regardless of how much data you have. If you want to change it, you may need to copy the data to another table where it has a new ordering. That said, ClickHouse has some ways around that. There's, for example, a feature called projections, where within a single part in the table, so tables again are divided up into parts, to make them possible to manage over many nodes or for very large tables, you can actually have different sort orders within the part using something called projections, which are different ways of arranging the same data, so that the queries, depending on what the question you're asking, you may use the original data, or you can use a projection on it.
So projection is actually like materialized file, right?
That's right. It's a different way of materializing the data, and it's a concept which I don't know if it's older than this, but it I first saw it in Vertica, or actually there's an academic project that preceded it called C-Store, which had this notion, and actually a really brilliant one idea. This is Mike Stonebreaker, who's sort of has probably written more different kinds of databases than anybody else on the planet. This was an idea he and his team came up with that was they were trying to trying to kill two birds with one stone. They wanted to have high availability, which means you have multiple copies of data. But at the same time, they wanted to be able to have different arrangements of the data so that queries in one case could, so you could choose the arrangement to use, for your queries. So they had the bright idea, why not have multiple copies, but for example, allow them to be sorted or arranged or stored in different ways. It's an absolutely brilliant idea. I was actually in the Mike Stonebreaker came and visited us at VMware, and he was just explaining this idea, in a conversation. It was sort of like, oh my God, that is so smart. It was so it was a really, and that's basically how the idea of projections arose in Vertica.
Nice. So like that's such a simple way
Yeah.
on such a complex problem, like insane.
It turns out it has some problems because in fact, excuse me, in fact it can be very difficult to recover. If you did have to recover, sort of go to the other projection to recover the first projection, it turns out it can be very slow just because the arrangement of the data is different. So it turned out to be not as versatile, I think, as they had originally hoped, but it was still a brilliant idea, and it's still and the notion of projections is something that we use inside of ClickHouse.
That's nice. That's it. Like I guess it can be. It has its own use cases, like always, right?
Yes. Yeah.
It's always the solution is actually for some problem which people encountered and they wanted to
Yeah.
solve, and this actually solves some of them.
Yes, and it solves it very well. It's, I mean, and that's an example of where I said that people can move between different databases. If you understand the notion of something like projections, you will see this come up in slightly different ways, but the same underlying idea can come up in many different databases, and each time you see it, you say, oh, I know what's going on under the covers. I know what the problems it can solve. I know the problems it cannot solve. I can see the limitations or even disadvantages of using this. If you have that background knowledge, then you can move between different databases quite easily.
I guess in general, for any of distributed computing applications, right? If you know the generic works,
Yeah.
right, it can help you understanding what's happening on, like, I don't know, compared how Apache Spark handles, some of the computations, right?
Yes.
How it's in Chino and how it's,
Yes.
in ClickHouse. So
Yes.
just
Yeah,
stick
that's
the fundamentals.
absolutely. And so distributed systems background is really important. And I'll give you a really relevant example. ClickHouse is sometimes criticized because it doesn't make it easy to update data. But in distributed systems, and by that I mean databases where the data is very large, is spread over many nodes, and may change very quickly, may have data arriving very rapidly. Going out and finding a row and changing it is a very expensive operation. But the first problem is you got to find it. If you have data spread across dozens of nodes, going to the right node and updating it is going to be slow. And it also has a bunch of problems that have to do with ensuring that data is consistent. That you may need to hold blocks to be able to update this copy. So the answer in many cases for ClickHouse is we just don't do it. What we actually do when we have to change data is we use something called, ClickHouse has many different types of tables. We have something called a replacing merge tree. And the idea is that when you want to change a row or many rows, you just insert new rows, but you put a version number on them. And when ClickHouse queries the data, it's able to resolve the differences so the data effectively with the highest version number wins. And this is more expensive at query time, but it actually resolves the problem of having to. It avoids the problem of having to go find data and update it. When the updates arrive, which is a very expensive operation.
I
And
was thinking that you're gonna
that's a
suggest
real
something like this.
Yeah, that's a real distributed systems algorithm where you throw the data in, and then on read you decide at that time you resolve which data should be visible.
Yeah, it's like merge on read, I guess, is the name for, at least in the iceberg. If you're dealing with Spark or these things, it's like actual merge on read. And when you said exactly, like we insert the row with a version, I'm like, exactly, that's because you insert everything, max by or whatnot, good.
Yeah. And so if you have that distributed, this is what I love about it. This is one of the things that I find kind of addictive about ClickHouse is all these really delightful and very clever distributed algorithms are present there, just as they are in things like Iceberg or Spark or others. But they're fun algorithms, and once you understand them, it's kind of enlightening because you actually do understand the behavior. Moreover, and more importantly, you actually understand how to construct an application that will use these algorithms most effectively and give you data back as quickly as possible.
Yeah, that's true. Nice. I didn't know some of these things that were capable of doing before, like this, before actually knowing ClickHouse. So that's going to be a fun trip for me to figure it out.
Yeah.
By the way, what language is built ClickHouse on?
C++.
Okay.
It's and C++ is still strongly favored for high performance systems. It you could argue people do, should we be using C++ or should we be using a memory safe language like Rust? Well, C++, if you're careful, is pretty hard to beat, and mostly for speed. And ClickHouse was originally designed by Alexei Milovidov, who's, I would say, is certainly one of the best C++ programmers I've ever met. He's really outstanding, and he is very, very focused on performance, and has put a lot of effort, both himself, but also through the efforts of committers whose work he reviews, to ensure that ClickHouse uses the powers of C++ to make to return query results as quickly as possible. So ClickHouse has an incredible number of optimizations. We have literally dozens of different representations of hash tables, which are the most common data structure used to hold query results during joins or when you're aggregating. And so so C++ is very effective. It does require a very high level of expertise to use safely and effectively.
Okay. For me, it's I was thinking when you mentioned Rust and with all of the hype it's already getting, but I guess the issue in general is about the developers and people knowing efficient C++. Might that be an issue at some point? What's your thoughts?
Actually, it is. So for people using ClickHouse, it's not. You don't have to know. You don't have to know anything about how it's put together. And in fact, most ClickHouse applications tend to be written in language like Python, Node, JS, or some variant of JavaScript or Golang. Those are probably three of the top languages that people are using. But yeah, it does restrict the pool of people who can do this effectively. And interestingly, Eastern Europe, so in the United States, a very large number of programmers, including system programmers, ended up going for Java. So so many of the database systems that came out of the United States were written in Java or its variants. So, for example, Presto is written in Java. Hadoop, of course, was written in Java. In Eastern Europe, by contrast, they kept a C++ culture. There's a lot of gaming development, for example. That's gaming and databases actually have a lot in common because you have to have very, very fast engines to drive the game. So as a result, ClickHouse, which originally came out of Russia, is written in C++, in part because there was a pool of people who knew it very, very well.
Okay, that's true. Actually, I was thinking that in universities, like one of the core studies for the system designers, like actually like strong programmers,
Yeah.
actually learn C++. And I was like, when I had to go through some of the courses, I didn't learn C++, but I went over C and
Yes.
later Java. And I'm like, okay, that's interesting. And they said, like, yeah, in C++, it's complicated in a way. And for me as a math background, like you don't have to worry about it. You won't be doing anything like that.
Right. Although interesting, one of my daughters is a math major, and she took C++, which
Nice.
she was not impressed, but so she wants to stay more on the mathematics side of the house and less on the computer science.
Nice.
But she did take it, so we have something to talk about together.
Nice. I'm also thinking. I think I forgot to ask. I know that there are connectors specifically for the ClickHouse made. I think there is Apache Kafka one, which you set up as a table in a way, and it allows you, to consume
Yes,
the data.
exactly. So what this is this brings up a very interesting feature of ClickHouse, which is table engines. So this idea is not new. MySQL, for example, had table engines, and anybody who's used it, did you use MySQL?
I use, but more of a just check the data or like take it and move it somewhere else. It's more of a
Right.
data engineering perspective.
Right. So MySQL is from the beginning had table engines, which are really different ways to organize the tables. So there was one called MyISAM, which was the original table engine, and then it was superseded by the InnoDB table engine. The ClickHouse, but MySQL always had a relatively small number of table engines, and you wouldn't really switch between them. ClickHouse, by contrast, has dozens. And so the table engines really give you different ways of arranging and accessing data. And so merge tree is the kind of the workhorse engine for for big data. It has 6 variants that that you can use in differing circumstances. ClickHouse, but there are other very, very different table engines. The Kafka table engine is one of the most interesting. What it does is it takes a Kafka topic and wraps it and makes it look like a SQL table. So that instead of seeing, for example, JSON blobs, what you might see if you're an application reading off the topic, in fact, what ClickHouse can do is it can, assuming the JSON is simple, it can actually, first of all, make it look like columns. And, by automatically converting the JSON to the column representation. Second thing is when you do a select on the Kafka table engine, you're actually reading from the topic. So the data gets pulled from the topic, handed back to you, and then you go stick it somewhere safe. So the Kafka table engine does this automatically. And as a result, it's the basis of a kind of simple linkage that you can set up where the Kafka table engine wraps the topic. You will then have a target table where you want the table to land, and in between, use a materialized view. So a materialized view reads automatically from the input blocks from the Kafka table engine, transforms them, and puts them into the target table. So there's this is how ClickHouse builds automatic integration to Kafka.
Nice. So basically, it runs a streaming, basically KSQL kind of way, right?
It's
Where you
kind
run
of
a
like
SQL on
exactly.
that.
Right. That's exactly right. So you're running C. It is very KSQL-ish. So and for people who are listening, that's the language that runs on top of Kafka, and that can read blocks as they're coming through. Yeah, that's pretty
Nice.
much the idea. And the Kafka table engine takes care of some housekeeping, like, hey, wait for a second, or wait till you've got X number of thousands of rows before you sort of form a block and pass it off to the materialized view.
So it's a combination utilizing also ClickHouse, best approaches, right? Not write
Yes.
one by one, but I'll wait for
Right.
this, for
Exactly. Buffer.
block.
In fact, that's a really major feature of Kafka is it decouples the the rate of data input and the size of the blocks on the producer side from the consumer side. So it's one of the most. It is the simplest in many ways. Conceptually the simplest way that you can have a lot of people generating a lot of data at different times and in different amounts, but then you can read them into ClickHouse in very large blocks.
Yeah, you don't have to take care of the underlying infrastructure for that,
Right,
right? Wrap
right,
it in SQL.
right.
Everything is SQL now.
That's true. For better or worse, SQL is the language that people use to uh, to process data. Better in the sense that it's a common language that's used almost universally in data management. For worse, because the syntax was invented back in the 70s, and those were dark times for computer language syntax. And I think the for me, exhibit number one is if you're familiar with SQL window functions, the the syntax on them is about the most non-intuitive that you could possibly invent. I always have to go look up. When I have to do window functions, window functions for people who don't know them allow you to aggregate data and then do additional computation on top of it, like doing a running sum, for example, like the sum of values for the last 7 days, for every row of results you get. Um, Window functions do handle that, but at some intellectual cost to the programmer.
Yeah, it's like for me, it's always, okay, function over, why we have over there,
Exactly.
and
Yes.
then in
Yeah.
the should I put partition first or should I put order first? I'm like,
Yes.
I'll try this, run. No, it failed. Okay, so other way around.
That's pretty much how I do it. I realize I hope this is a safe place, but yeah, I have a confession that's exactly how it goes with me. I suppose if I use them more, it's a bit like Perl regular expressions. Uh, once you get them into your noggin, they seem very natural, but but until that time, you're going to be consulting examples to get it to work right.
Regular expressions, it's, I guess, a different beast. You have a cat
I,
walk over your keyboard and you have a regex.
Yeah, actually, though, regular expressions, to be fair, are really easy to understand. Because the idea is the concept behind them is quite clear. And in fact, it sounded like I'm dissing Perl, but I'm not. I still think they are. Those are those I can program those without having to look up anything. Um, they had a. I still think it was the best implementation within a language of regular expressions. Uh, the I haven't seen one better.
Nice. Yeah, but like I guess like always, right? Everything has a specific purpose, right?
Yes. Yeah.
So think what you're choosing when you're choosing, and
Right.
that's good.
Yeah. I don't think
Oh,
too many people choose Perl anymore. It's kind of
uh,
faded as a language.
it's like COBOL, I guess, in a
Yeah.
way, right? Where only certain areas have it, and then they have to find people and uptrain them, to use it.
Right.
Or there are
Right.
some hardcore fans which are actually, writing
Yeah.
something in them.
Yeah. I'm sure there are people who's I mean, because it's still present on Linux systems, and it's a very versatile language. I just found it after a time. I found it was overall it's not a particularly productive language for me. Because it's kind of hard to use. I think there are other languages that are much easier to write applications in.
True. Okay. So, thank you, Robert. And last question, since I see your background is a huge bookshelf of very nice books. So, would you have any recommendations for the listeners?
Yeah, that's a great question, because what's kind of sad is the people don't use books as much as they used to for programming. I will say, just a second, let me have a quick look in here. I see
Okay.
if I can find one of my favorites. Yeah, I got it. It was ready to hand. So this book is called Java Concurrency in Practice, and it's by Brian Goetz. This isn't a very current book. I think it's probably now easily 15 years old, but it described how to use concurrency, the concurrency features of Java. For example, threads, thread pools, um, locks, all that kind of stuff. And the reason I like this book is it was the first. It has a really great introduction to the Java memory model, which is like in Java, when you acquire a monitor, when you do a wait on a Java object, when you read it, it means the contents are synchronized so that whoever wrote it last, whoever held the lock last and put data in, when you get that lock, you're guaranteed to see the same data that they wrote. Now, that doesn't seem very profound, except that it works even when even when the process that wrote it was running on like a different CPU, different cores, had saw a different view of system memory. This is all handled automatically. And so, for example, there's a concept in CPUs called memory barriers, where you synchronize memory contents between threads. By understanding the Java memory model, it was completely enlightening, because it was the first time I understood this concept, like what's actually going on in the CPUs. I love this book. I read it in a train. I was going to a conference, and I was taking the TGV, which is the French high-speed train, over the Alps. So it was really beautiful. I was sitting in the train reading this book and becoming enlightened. The Alps are sort of going by the window, and I was becoming enlightened on how memory works in modern CPUs. That's a book I still refer back to, when I have to think about this. So there are many great ones. I think some of the older ones, there's obviously The Art of Computer Programming. There are things like Jim Gray, Transaction Processing. That's an older book written in the early 90s, but again, one that I read many, many times and is still relevant today. So there's a lot of really good stuff out there. And
Yeah,
I've just collected
nice.
them over the years.
All of them are read, right? That for
Yeah,
sure.
every single page. No, Arctic Knuth, I really only open Knuth in two cases. One, I'm completely stuck. I just have no idea to think about something, so I go look and see if Knuth has something good to say. Or if I'm doing something that's so stupid simple that it can't possibly be done wrong, I sometimes also look at Knuth as well, because it turns out that something like linear search, which you'd think, okay, how hard could that be? Well, it turns out there's some really interesting, depending on, like your constraints, linear search is actually, there's more to it than you think. And if you go read the description in Knuth, I think there's 15 or 20 pages on that, where you become enlightened about just how how to do it right, and how to make sure you're not missing something.
Nice. So, yeah, thank you for your time. It was very smoothly, and I'm super excited to have picked your brain about
Yeah.
ClickHouse capabilities, and how it works under the hood, and these things, and as well for the book recommendation.
Yes.
So
Yeah, enjoy. So I'm sure Brian Goetz would appreciate the recommendation. Thank you again, Thomas. It's been wonderful being on your show.
yeah, thank you, and have a nice Friday.
Same to you.